Welcome to the Deep Dive, the show where we take your burning questions, the fascinating sources you bring us, and our collective curiosity, transforming information overload into crystal clear understanding. Today, we're plunging into something so fundamental, so omnipresent, that we often overlook its incredible complexity. The very buildings that shelter us, where we live, work, and play. This is a deep dive into the house and its parts, and the profound methods of construction. Our mission today is to peel back the layers of a seemingly simple structure, like your own home, and uncover the intricate engineering and thoughtful design beneath its surface. You might walk into a room and just see four walls, a floor, and a ceiling. But after this deep dive, you'll understand the dynamic, interconnected systems that allow those walls to stand proudly, to shelter you from the harshest weather, and to function as truly livable spaces. We're going to reveal how diverse components, from the hidden giants beneath your feet to the very visible roof overhead, work in absolute concert to create the comfortable, safe, and functional environments we inhabit every single day, all expertly guided by the incredibly detailed sources you've provided us.
And that, for me, is the true magic of this kind of exploration. It's genuinely surprising how much profound insight you can gain by simply looking more closely, more thoughtfully, at something we interact with on an hourly basis. A building is far from a static object. It's a dynamic marvel of engineering, a testament to humanity's ingenuity in understanding physical forces, material science, and our fundamental needs for shelter and comfort. By the end of this deep dive, you won't just be able to label various parts of a building. You'll understand their individual purpose, their vital connection to the whole, and most importantly, why they matter for your safety, your comfort, and the long-term functionality of any structure. It's about appreciating the silent, tireless work that goes into crafting every single building around us, making them truly habitable and enduring. The building's a unified system, beyond bricks and mortar.
Okay, let's unpack this. When we look at any building, be it a cozy cottage, a bustling office tower, or a grand civic hall, our initial perception is often of a singular, solid, almost monolithic entity. We see a house or a school. But the sources you've given us immediately challenge that perception, telling us quite clearly that a building is far, far more than that. It's described, and this is quite a mouthful, as a physical embodiment of a number of necessarily related, coordinated, and integrated systems. That sounds incredibly academic. So for us, for you listening, what does this truly mean in practical, tangible terms? Is it just jargon, or is there a fundamental shift in how we should perceive buildings embedded in that definition?
That's an excellent question, and it's absolutely not just academic jargon. It's the very core concept. It means precisely what it says. Every building is a complex symphony of interconnected parts, each playing a vital, interdependent role. The phrase unified system is incredibly key because it emphasizes that individual components are never isolated. They are interrelated and articulated. Think of it like a living organism, perhaps the human body. You have a skeletal system providing support, a circulatory system delivering life, a nervous system for communication, all working together seamlessly, constantly communicating and adapting. A building is strikingly similar.
Ah, okay, that analogy helps. So not just a pile of parts, but parts working together.
Exactly. The general objective of building materials and methods of construction isn't merely to stack bricks and timber in a pretty way. It's about designing and assembling components to create an overall physical image that makes coherent sense, where all the major components are fitted together with a deliberate purpose designed to endure. Our sources elegantly break down this building into two main, overarching components that embody this systemic approach: the enclosure and the service utilities.
Enclosure and service utilities, got it.
These two components, working in perfect tandem, achieve the building's fundamental purpose, providing a controlled, safe, and ultimately a comfortable environment for human activity. Without this meticulously coordinated integration, a building would quite literally just be a pile of inert materials, not a habitable living space.
It's the difference between a pile of bricks and a home.
Precisely. A, the enclosure, defining the space.
So if the building is this complex organism, the enclosure sounds like its protective skin and skeleton, its very boundary. Our sources define it as the means of containment and articulation of a habitable space. Containment and articulation, that sounds like it's doing a lot more than just keeping the rain out, doesn't it? What does that truly involve for us as occupants?
You're absolutely right. It's far more sophisticated than a simple box or a basic shelter. The enclosure is critical because it defines the physical limits of the building, separating the carefully controlled interior environment from the unpredictable exterior.
Yeah.
But it also meticulously organizes the interior itself, carving up that larger volume into functional private or public spaces. It's made up of three general assemblies, each with a very distinct, crucial, and often surprising function.
Okay, 3 parts to the enclosure. What's the first one?
First, we have the means of support. This is the fundamental, often unseen skeleton of the building its bones, if you will. Its definition is precise and powerful. It's the framework that maintains the enclosure in its shape and is intended while resisting all external and internal forces acting upon such enclosure.
Resisting forces like gravity.
Exactly. Crucially, its ultimate function is to transmit all such forces to the ground. This isn't just about holding the roof up against gravity. It must actively resist the constant, relentless pull of gravity, which engineers meticulously calculate as dead loads, the sheer static weight of the building materials themselves, like concrete, steel, and timber.
Okay, the building's own weight.
Right. And live loads, the dynamic, ever-changing weight of occupants, furniture, snow on the roof, or even a sudden burst of wind. But beyond gravity, it also resists more dynamic, violent forces like the forces of wind pressure, the subtle vibrations from nearby traffic or machinery, and even the catastrophic forces of earthquakes.
Wow, okay, so it's dealing with a lot. How does it actually transfer those forces?
If you look at the load diagram you provided, you can vividly see this force transmission in action, a continuous, unbroken chain. Forces from the roof are first transferred to the roof trusses, then through roof beams, meticulously channeled down through columns and beams, through the structural slab of each floor,
Working its way down.
eventually reaching the massive wall and column footings, and finally, safely into the ground. It's a marvel of engineering, an unbroken chain of force transfer, meticulously designed to keep the entire structure stable and intact under the most diverse and extreme stresses.
So without that robust means of support,
Without it, a building is simply a precarious stack of materials waiting to collapse.
and then literally on top of or wrapped around that vital support system comes the envelope. That's the skin of the building, right? The part we usually interact with most directly from the outside, the part that gives a building its outward appearance.
Exactly. The envelope is defined as the physical barriers and/or selective, and to all external or internal environmental forces acting upon such enclosure. Its primary function isn't just to be a barrier. It's a sophisticated mediator. It's the assembly that comprises the roof and the exterior walls, essentially the building's entire protective skin, and it is precisely designed to mediate the immediate environment.
Mediate. What does that mean in practice, like a filter?
Precisely. What does that truly mean for you, the person inside? It means it acts as a smart filter. It protects you against, or selectively allows for, external environmental factors that would otherwise make the interior uninhabitable. Our diagrams beautifully illustrate this. Think about rain, relentless wind, humidity, or even the incessant drone of city noise. The envelope acts as an impermeable barrier, keeping these elements out, ensuring a dry, calm, and quiet interior.
Keeping the bad stuff out.
But it also intelligently mediates heat and light. Windows, for instance, allow precious natural light to flood interior spaces, reducing the need for artificial lighting. But a well-designed envelope will also control heat gain or loss, absorbing beneficial solar radiation in winter and reflecting unwanted heat in summer. This mediation is crucial for thermal comfort and energy efficiency.
So it's not just a dumb wall, it's actively managing things.
Exactly. It's not just a passive barrier. It's an intelligent, active filter, constantly working to maintain a comfortable and stable internal climate, regardless of what chaos might be raging outside. It fundamentally shapes your comfort, energy consumption, and even your mood within that space.
That makes perfect sense. So we have the structure holding everything up, the sophisticated skin protecting it from the outside world.
Yeah.
And then what about inside? That brings us to the elements of interior. These are the parts that carve up the vast open volume into specific functional spaces, yes?
Precisely. The elements of interior are defined as the planes that define the interior, while also cleverly resisting internal environmental factors. This assembly includes the ceiling, floor, partitions, and the means of circulation or conveyances such as stairs and ramps.
Okay, so walls, floors, ceilings, stairs. Basically everything defining the inside layout.
Yes, and it's important to recognize that even these internal elements contribute significantly to the building's overall enclosure function. They don't just provide aesthetic divisions or visual privacy, they play a crucial role in shaping the living or working space, defining how people move through it, and critically, how sound and temperature behave within the building. Think about how a solid internal wall can block the sound from a noisy room, creating acoustic separation, or how a well-insulated partition can help keep one room warm while an adjacent one is cooler.
Right, so they manage the internal environment too.
Exactly. They help to create those specific, comfortable, and functional zones within the larger structure.
The lifeblood of the building.
So, the enclosure gives us the essential shell and the underlying structure that makes a building stand firm and safe, mediating its relationship with the outside world. But what about making it truly, dynamically livable? That's where service utilities come in, right? These are the hidden networks, the vital arteries and veins that power our lives within those walls.
Absolutely. The enclosure provides the robust framework, but the service utilities are the absolute lifeblood, the nervous system, defined as the means of maintaining the environment within the enclosure at comfort and safety levels. These are the indispensable systems that deliver the essential functions we often take completely for granted, until, of course, they stop working.
Yeah, you notice the plumbing when it leaks.
Exactly. Our diagrams provide excellent, clear examples of these vital networks. First, there are the electrical utilities. This encompasses everything from the lights that brilliantly illuminate our spaces, allowing us to function day and night, to the ubiquitous power outlets we plug our myriad devices into.
Right, power points everywhere.
The simple switches we flip to control lighting and power, and the complex circuit breaker panel that acts as the guardian, protecting the entire system from overloads and short circuits. Without electrical utilities, a building simply isn't functional in the modern world. It would revert to a pre-industrial state.
Pretty fundamental stuff. What else?
Then we have mechanical utilities. These systems are primarily about environmental control and ensuring our comfort. Think about the hum of a room air conditioner unit cooling us on a sweltering summer day, the gentle whir of cooling fans circulating air, or the warmth emanating from heating systems keeping us cozy in winter.
So heating and cooling, ventilation.
Exactly. These systems don't just move air, they actively manage temperature and airflow, directly regulating the indoor climate to make the enclosed space truly comfortable, healthy, and productive for its occupants. They are the lungs and temperature regulators of the building.
Okay. And plumbing. We mentioned leaks.
Next up are plumbing utilities. These are utterly crucial for public health, sanitation, and basic human dignity. This intricate system includes the network of water pipes delivering fresh, potable water throughout the building for drinking, cooking, and bathing, as well as the equally vital sanitary drainage pipes carrying wastewater efficiently and hygienically away from the building. And of course, the fixtures we use daily, like water closets and lavatories, are the visible points of this hidden, complex system.
Water in, waste out. Essential.
Vital. These elements are not just convenient. They are vital for sanitation and supporting basic human needs, profoundly impacting the quality of life within any structure. And in today's increasingly interconnected world, communication utilities are truly indispensable. This broad category covers traditional telephone lines that still provide essential connections, sophisticated intercom systems for internal communication within larger buildings.
Like in apartment blocks.
Right. And, perhaps most critically now, the vast wiring and infrastructure necessary for high-speed internet connectivity and computer networks. These systems facilitate instant communication both within the building itself and, crucially, with the outside world, making modern commerce, education, and social interaction possible.
Wi-Fi, basically. Can't live without it.
Pretty much. Finally, and perhaps most critically for the well-being of occupants, are the safety and security utilities. This category encompasses essential protective measures that offer peace of mind and, in emergencies, save lives. This includes life-saving devices like smoke alarms that detect the earliest signs of fire, robust fire alarm systems that warn all occupants to evacuate, and burglar alarms that protect property and deter intruders.
Fire alarms, smoke detectors, security systems.
Exactly. These systems are absolutely crucial for occupant safety, for mitigating damage, and for property protection. All of these services and utilities, though often meticulously hidden behind walls and under floors, are profoundly integral to a building's dynamic functionality and its very habitability, transforming a mere structure into a responsive, secure, and truly livable environment. 2. Ground up. Foundations and floor systems.
Okay, we've got the big picture now, how a building functions as an integrated system, its enclosure acting as skin and skeleton, and its services as its vital organs. Now, let's literally go from the ground up, following the logical sequence of construction. Our sources lead us to the very beginning. Foundations. Here's where it gets really interesting, because this is the ultimate unsung hero, the part you rarely, if ever, see, yet it's where everything else gets its unwavering support. If the foundation isn't absolutely right, nothing else above it truly matters.
You've hit on the most crucial point in all of building. Foundations are, quite literally, the base upon which all else rests, supporting the colossal weight of the entire structure. They are precisely defined as the lowest support on which building rests. And it's no accident, no mere coincidence, that they are typically made of reinforced concrete. This material choice is incredibly deliberate and utterly vital because foundations are tasked with the immense responsibility of carrying the weight of the entire building.
All that weight. The dead loads, live loads, wind, everything.
Everything. This means the massive dead loads of the structure itself, every beam, every wall, every roof tile, the live loads of its occupants and contents, and all the environmental forces we discussed earlier, like relentless wind, the shifting ground from seismic activity, or even snow loads, are all meticulously channeled down to the foundation, which then transfers them safely and evenly into the earth below.
So what are the actual parts of the foundation doing that?
The foundation itself is a carefully engineered system comprised of essential parts working in concert. The first, and perhaps most critical, is the footing. This is defined as the widened part of the base of the column or wall.
Widened. Why?
Its primary and indispensable importance is to spread the load over a greater area to prevent or reduce settling. Imagine for a moment trying to stand a massive skyscraper on a single tiny point. It would simply sink into the ground, or worse, tilt and collapse.
Oh, okay. Like snowshoes for the building.
Exactly, a
Right.
great analogy. The footing brilliantly distributes that immense pressure, that colossal weight, over a much larger surface area of the soil, ensuring the building remains stable, level, and doesn't settle unevenly over time, which could lead to severe structural damage, like unsightly cracks in walls or even catastrophic failure.
Gotcha. And what connects the building to the footing?
Connected to the footing, often extending upwards from it, is the column or pier. This is described as a relatively slender structural compression member, usually vertical, supporting a cord.
So the vertical post, basically.
Yes. Its function is straightforward, yet absolutely critical. It's the robust vertical element that diligently transfers the loads from the beams, floors, and walls directly above it straight down to the footing. It acts as a crucial intermediary, a strong, unyielding link in that unbroken load transfer chain we discussed earlier, ensuring that all forces are safely and efficiently directed towards the ground. B foundation and floor system for wood construction methods.
Our sources and the diagrams you've shared show a very specific setup for wood construction, which is incredibly common in residential buildings across many parts of the world. What's distinct about how foundations and floors interact here, particularly using those concrete elements as a crucial base for what becomes a much lighter wood structure above? It's a fascinating hybrid.
It truly is a common and remarkably effective hybrid approach, balancing the inherent strengths of different materials. The base is still uncompromisingly solid, providing unwavering stability, but it then transitions elegantly to a more lightweight, yet still robust, and often more flexible wood system above ground. At the very bottom, ensuring that initial unyielding stability, you still find the reinforced concrete footing. This provides that solid, immovable base and is often internally reinforced with the latticework of steel rebar, known as bar matting, for added tensile strength, preventing it from cracking under load.
Okay, so concrete footing still in the columns.
Extending up from that footing, you'll typically find the column reinforcement, which refers to the meticulously placed vertical steel bars and horizontal ties within the concrete columns, providing the necessary strength and ductility to withstand various forces. On top of that concrete pier or column, a post, specifically a wooden post, is meticulously set atop with masonry post, or reinforced concrete pier, acting as the crucial transition point from the unyielding concrete foundation to the more adaptable wood framing that forms the upper structure of the building.
Ah, so that's where the wood starts.
Right. Then, running horizontally, we encounter the girder. This is typically the main horizontal beam where the floor joists and the posts together distribute the load. It's a significant structural member, often spanning longer distances, that ties everything together horizontally, gathering the loads from the floor system and transferring them efficiently to the posts and columns below.
So the girder supports the floor beams.
Essentially, yes. Spanning between these sturdy girders and posts are the floor joists, which are defined as parallel beams used to support the floor. Our diagram clearly indicates they are often precisely spaced at a specific interval, such as 400 millimeter OC, meaning on center.
400 millimeters on center.
Wait.
Wow, that's spacing.
This on-center spacing isn't an arbitrary number. It's a sweet spot found through centuries of building, balancing crucial factors like strength, stiffness, cost, and efficiency. Go much wider and your floor might feel uncomfortably bouncy, or worse, unsafe. too narrow, and you're potentially over-engineering, wasting valuable material and adding unnecessary cost.
Right, the Goldilocks zone for floor joists.
Pretty much. This seemingly small detail is a fundamental principle of how we meticulously create floors that feel absolutely solid and dependable underfoot. To provide additional stability to these joists and prevent them from twisting or buckling under load, especially over time, we use floor cross bridging, diagonal or perpendicular bracing installed between the joists.
Okay, keeps them straight.
Exactly. And finally, on top of all this intricate framing, you have the actual surface of the floor itself, often T&G flooring, which stands for tongue and groove flooring, where the individual floorboards interlock neatly to create a smooth, continuous, and durable walking surface.
Tongue and groove, yeah, I've seen that.
This system elegantly demonstrates how robust, unyielding concrete elements provide the fundamental base, then transition to lighter yet incredibly strong wood framing for the upper levels, combining unparalleled strength with remarkable construction efficiency. See foundation and floor system for reinforced concrete construction methods.
And for reinforced concrete construction, which we commonly see in much larger or multi-story buildings, it looks quite different from the wood frame system. What's the key distinction in how the foundation and floor systems are built here, and what does that imply for the building's capabilities?
The distinction is profound and primarily lies in its monolithic nature and immense inherent strength, specifically designed to handle much heavier loads and span far greater distances. Just like with wood construction, it all begins with a column footing at the very base, providing that essential broad support to meticulously transfer the building's colossal load to the ground. Rising directly and seamlessly from the footing is the column, which serves as the main vertical support, all uniformly made of reinforced concrete.
So concrete columns directly on concrete footings.
Yes. Connecting these columns horizontally are robust beams, also meticulously constructed from reinforced concrete. These are the primary horizontal structural members that link the columns, forming a rigid grid, and crucially, they primarily support the structural slab.
The structural slab, that's the floor itself.
Right. The structural slab itself is the solid, thick, reinforced concrete floor, serving as the primary horizontal load-bearing element. Unlike the wood system where individual joists support individual planks, here the entire floor is a single, incredibly strong, cast-in-place concrete element, often poured as one continuous unit.
So it's all one piece, basically.
Essentially, yes. This comprehensive system is renowned for its exceptional rigidity, its long-term durability, and its unparalleled ability to handle truly significant loads, making it the ideal choice for multi-story buildings, large commercial structures, industrial facilities, and anywhere a remarkably robust, fire-resistant, and vibration-dampening floor is required.
So much stronger for bigger buildings.
Exactly. It's a much more integrated, cast-in-place system from the very ground up, engineered for resilience and scale.
And whether we're talking about wood or concrete construction, the floors themselves are absolutely critical. They're not just something we walk on. They're the fundamental horizontal boundaries that meticulously define the interior spaces, separating one level from another, and they have their own set of specific important parts.
Indeed. Floors, in this comprehensive context, refer to the entire intricate framework that robustly supports the walkable surface, often concealing a lot of engineering beneath. Our sources describe them as comprising of the following parts. First, we have the girders, which are the beams which support the floor joists and tie the posts together. These are the primary heavy-duty, load-carrying horizontal members, acting as major collectors of weight from the floor system and channeling it to the vertical supports.
The big beams.
Right. Then, building upon those girders are the floor joists. These are a series of parallel beams used to support the floor. As we observed in the wood construction methods, these are typically spaced at regular, calculated intervals to distribute the weight of the occupants, furniture, and any dynamic loads evenly across the floor's span.
The smaller, repeating beams.
Correct. And finally, the flooring itself, which is quite simply the material that is used to cover the floor. This is the actual surface we see and directly interact with every day, whether it's elegant hardwood, durable tile, plush carpet, or polished concrete, and it's laid directly over the joists or the structural slab.
The part you actually step on.
Exactly. Each component here, from the hidden structural elements to the visible surface, is carefully selected, precisely measured, and meticulously assembled to create a stable, durable, aesthetically pleasing, and ultimately functional surface upon which we live our lives. 3. Defining space. Walls and partitions?
So once we have that incredibly strong and stable base, that foundation and floor system, the next logical and essential step in defining our living or working environment is to create the enclosed specific spaces themselves. That, of course, brings us to walls. They're much more than just flat surfaces that passively keep the weather out, aren't they? Our sources brilliantly show us different ways to build them, depending on the chosen material, and each method has its own distinct components, its unique structural integrity, and its specific implications for the building's overall performance.
That's perfectly articulated. Walls truly serve a multifaceted purpose. They form the fundamental exterior framework of the building, providing its protective outer skin, its form, and its primary structural integrity. But equally important, they also partition the interior into individual rooms, functional zones, and private areas, defining the flow and utility of the space. The choice of material and method for wall construction significantly impacts a wall's performance across various crucial metrics, from its inherent load-bearing capacity and its ability to resist external forces, to its insulation properties, its acoustic performance, and fundamentally how it interacts with all the other integrated building systems.
Right, so the type of wall matters a lot. Let's start with wood walls, a wooden wall framework. Our diagram for the wooden wall framework shows a fascinating, almost skeletal grid. It looks incredibly efficient. What are all these individual pieces, and how do they precisely come together to form a complete, robust wall that stands strong against the elements?
It is indeed a remarkably efficient and ubiquitous method, especially for residential homes and many light commercial buildings, offering a balance of strength, flexibility, and cost-effectiveness. It all begins at the very bottom with the sole plate. This is a horizontal timber which serves as the base for the vertical studs. It's typically anchored directly and securely to the foundation or the floor system below, providing an unyielding, level sill upon which the entire wall framework will be erected.
Okay, the bottom piece.
Right. Rising vertically and forming the primary skeletal structure of the wall are the vertical studs. These are the upright and transverse timbers that act as supporting element in a wall or partition. They are the main vertical load-bearing elements in the wall, running continuously from the sole plate at the bottom to the cap plate at the top, meticulously transferring vertical loads.
The upright 2x4s you usually see.
Exactly, those are typically the studs. Interconnecting these vertical studs, you often find horizontal studs. These timbers connect the vertical studs laterally, providing essential bracing, forming headers and sills for openings like windows and doors, and crucially offering solid attachment points for both interior and exterior walling materials.
Okay, so horizontal pieces for strength and openings.
Precisely. Capping off the entire framework at the top is the cap plate, which is the top horizontal timber that effectively ties all the vertical studs together, creating a unified, rigid top edge for the wall. This plate often serves as a critical bearing surface for the floor joists or roof system directly above, ensuring seamless load transfer.
So bottom plate, vertical studs, horizontal bits, top plate. That's the frame.
That's the core frame. Once this robust framework is meticulously complete, it's ready for its protective and aesthetic skin. You then have the exterior walling, which is the outer material meticulously covering the framework. This could be anything from traditional siding, durable brick veneer, or smooth stucco, providing the crucial weather protection, enhancing the building's thermal performance, and, of course, lending it its distinctive aesthetic appeal.
The siding or brick on the outside.
Correct. And on the inside, there's the interior walling, which covers the framework to create the finished, smooth room surface, typically drywall or plaster.
Drywall, yeah.
This comprehensive system, relying on lightweight but incredibly strong dimensional lumber, forms a versatile, adaptable, and surprisingly robust framework that has been the backbone of countless structures for centuries. B. Concrete hollow block wall, CMU.
Concrete hollow blocks, or CMUs. We see these used so widely, from simple garden walls to the core structures of many buildings. How is this construction method profoundly different from wood framing, and what truly gives it its incredible strength? It looks like there's much more to it than just stacking blocks on top of each other.
You're absolutely correct. There's a sophisticated engineering behind it that goes far beyond simple stacking. A concrete masonry unit, CMU, is, as our source defines, a manufactured building unit of stone, clay, or concrete block. On its own, a CMU is incredibly strong in compression. It can bear immense weight pressing directly down on it. But its real dynamic strength, its ability to resist forces that would pull or bend it, comes from its meticulous reinforcement.
Reinforcement. Like steel bars.
Exactly. The diagram clearly shows this. Steel bars, commonly known as rebar, are precisely inserted both vertically and horizontally within the hollow cores of the blocks and then solidly grouted in place with mortar or concrete. This rebar provides critical tensile strength, making the wall much more resistant to lateral forces like the immense pressure of strong winds, the shifting ground during seismic activity, or even simply the building settling.
So the steel stops it pulling apart.
Precisely. Without this reinforcement, CMU walls would be much more vulnerable to cracking and collapse when subjected to these dynamic forces. Above any openings in the wall, such as windows or doors, there's a vital, often understated structural component called the lintel beam. This is a horizontal structural member over an opening which carries the weight of the wall above it.
Ah, the beam over the window or door.
Right. Imagine if you just cut a hole in a block wall, all the blocks above would simply fall. The lintel bridges that gap, effectively redistributing the load around the opening. If a lintel isn't properly installed or sized, you'll see telltale cracks radiating from the corners of your windows and doors.
Okay, very important piece.
Absolutely. Then, at the very top of a masonry wall, especially an exterior one, you often find coping. This is a concrete beam that tops a masonry wall, serving a dual purpose. It provides a clean, finished aesthetic edge, but critically, it protects the wall below from water penetration by shedding rainwater away, and often helps to distribute loads from the roof or floor system above uniformly.
Sort of a cap for the wall.
Exactly. And of course, the entire CMU wall, just like our columns, must rest on a wall footing, which, similar to column footings, spreads the wall's concentrated load to the ground, preventing any uneven settlement. Now, our sources mention a water trowel and a Weepmer board. It's highly likely these are typos in the original source, and the terms intended were water table and weep hole board, or simply weep holes. Let's clarify those as they're fascinating.
Okay, typos happen. What's a water table?
A water table is typically a horizontal projection, often a piece of board or masonry placed at the bottom of the wall that deflects water away from the foundation, much like a miniature roof for the base of your wall. It's designed to make sure rainwater running down the wall sheds clear of the joint where the wall meets the ground.
Got it. Kicks the water away. And weep holes. Sounds strange.
And the weep hole board, or more commonly, weep holes themselves, are truly subtle but critical details. These are tiny openings, small gaps, strategically placed at the base of masonry walls, often above the water table or at the bottom of the wall cavity, that are designed to let any trapped moisture out from within the wall system.
Let moisture out. Why would moisture be in the wall?
Well, masonry can absorb moisture or condensation can form inside the wall cavity. Weep holes prevent that water from accumulating inside, which could lead to rot, mold, or structural damage over time. It's a brilliant example of how even the smallest, almost invisible details protect against the relentless, destructive power of water, ensuring the long-term durability of the structure.
Wow. Tiny holes, big job.
Exactly. This method, especially when properly designed and meticulously reinforced, provides exceptional structural integrity for incredibly robust, durable, and fire-resistant construction.
Dividing the interior.
Beyond the main exterior walls that give the building its shape, provide its protection, and bear its primary loads, buildings also have numerous internal walls. Our sources categorize these as partitions, and they serve a profoundly important yet often misunderstood function in organizing and defining the interior space.
They absolutely do. Partitions are simply defined as inner walls dividing the structure into rooms. While they might seem less critical than those mighty exterior walls that resist external forces, their role in defining functional spaces, providing privacy, and controlling acoustics within the interior is immense. Crucially, there are two distinct kinds that you must be aware of, especially if you're ever considering renovations, remodeling, or any modifications to a building. Knowing the difference can literally save you from structural disaster.
Okay, two types. What are they?
First, we have the non-load-bearing partition. As the name clearly suggests, these are used only to separate one room from another. The key insight here is that they do not carry any structural weight whatsoever from the floors or roof above.
So they just divide space, they don't hold anything up?
Correct. This means they are purely for spatial division. Because they are not integral to the building's structural stability, they can often be removed or altered with relative ease, offering significant flexibility for interior layout changes without compromising the building's integrity. Think of moving a closet wall in your bedroom. It's likely non-load-bearing.
Right, easier to change. What's the other type?
In stark contrast, there's the load-bearing partition. These are far more significant and demand absolute respect because they help carry the weight of the structure directly above it.
Ah, okay. These ones are holding things up.
Yes. These walls are absolutely integral to the building's support system, acting much like internal columns or beams. They are part of that continuous load path, efficiently transferring weights from upper floors, or the roof, all the way down to the foundation. Knowing the difference between these two types of partitions is paramount for any building modification project. Removing a load-bearing partition without first providing adequate, properly engineered alternative support can lead to immediate and potentially catastrophic structural failure, causing floors or roofs to sag, crack, or even collapse.
Wow. Okay, definitely need to know which is which before knocking down walls.
Absolutely critical. So while they both divide space, their structural roles are fundamentally different, which directly impacts not only their flexibility for future changes, but more critically, their contribution to overall building stability and safety. 4. Overhead protection. The roof is
If the foundation is the lowest support, literally connecting the building to the earth and anchoring it against the forces below, then the roof is its direct, majestic counterpart, the ultimate top cover, the primary shield protecting us from the relentless elements above. But this isn't just a simple lid, is it? Our sources showed that a roof system is an incredibly complex assembly in itself, a fascinating puzzle of interconnected parts, especially when you peer into the intricate world of its framing.
You're absolutely right. It's a sophisticated marvel of structural design. The roof is comprehensively defined as the framework that acts as top cover of the building. It's designed not just to keep out rain and snow, but to heroically withstand immense wind uplift force that try to rip it off, the immense weight of accumulated snow, and even the lateral forces transmitted during seismic activity.
Wind uplift, trying to pull the roof off.
Exactly. Wind moving over a roof creates low pressure, which can generate significant lifting forces. The roof structure has to resist that. Furthermore, a well-designed roof system is crucial for managing heat and light, contributing significantly to the building's energy efficiency and interior comfort. Its effectiveness, its very ability to protect, relies entirely on the intricate relationships and precise connections between its many components, particularly within its framing system, a roof framing system.
Our diagram for the roof framing system looks like a fascinating puzzle of triangles, repeating over and over. It's clearly designed for immense strength, almost like a giant inverted bridge. What are all these interconnected pieces, and how do they work together to form such a robust, unyielding cover over our heads?
That triangular arrangement is no mere aesthetic choice. It's the cornerstone of structural engineering efficiency. Triangles are inherently rigid and incredibly efficient shapes for transferring loads, making them ideal for spans. The primary component you immediately notice, forming the backbone of this system, is the truss. This is defined as a braced framework, usually in some triangular arrangement, and used to hold up the roof.
The big triangular frames.
Right. Trusses are brilliantly engineered to span wide distances efficiently, effectively channeling all those roof loads, snow, wind, the weight of the roofing material itself down to the walls below, minimizing the need for internal support columns. They are designed to act as a single strong unit. Supporting these trusses, or sometimes directly supporting rafters in simpler roof designs, are girts, which are the horizontal member between posts and support the truss or rafter.
Yeah.
If you look closely at non-truss roofs, you'll also clearly see rafters, which are an inclined member that supports the roof. These are typically individual beams that run from the ridge, the very peak of the roof, down to the eaves, the overhang.
So rafters are the sloping beams.
Correct. To securely anchor the horizontal elements to these inclined ones, especially where they meet, you have small but mighty components called cleats, which are specifically used to anchor the purlins to the truss or rafter, ensuring they stay securely in place against gravity and uplift forces. For additional stability and to prevent the bottom of the trusses from spreading outwards under load, particularly in larger roof systems, there's the stretcher, which is the horizontal member placed between the bottom cords of two trusses and served to steady the lower part, effectively bracing them.
Okay, more bracing.
And enhancing the overall rigidity of the entire roof system, ensuring it acts as one cohesive unit, you'll find truss braces. These are diagonal members that connect the bottom cord of one truss to the apex of another truss and are vital for stiffening the upper part of the trusses. These diagonal elements lock the trusses into a stable, three-dimensional system, preventing lateral movement or racking during high winds or seismic events.
So lots of interconnected pieces making it strong.
Absolutely. Directly supporting the roofing material itself are the purlins. These are horizontal members, often spaced at precise intervals, usually at 700 millimeter OC on center, that run perpendicular to the rafters or trusses. They provide the nailing or attachment surface for the actual roof covering, ensuring it has continuous and even support.
The bits the actual roofing sits on.
Yes. Our diagram also thoughtfully shows roof insulation. an incredibly important layer providing crucial thermal protection, helping to regulate indoor temperatures, keeping heat in during winter and out during summer, which translates directly to energy savings and comfort for the occupants.
Insulation is key.
Definitely. The outermost protective layer, the part that directly sheds water, is often GI sheeting or galvanized iron sheeting, a very common and durable roofing material in many climates. To seal the very peak of the roof where two slopes meet, preventing water ingress, there's the GI sheet ridge roll.
The cap on the top ridge.
Right. And along the critical edges, meticulously protecting them from water penetration and providing a clean, finished appearance, you have GI roof end flashing, which is specialized metal work designed to divert water away from vulnerable joints. Finally, there are the elements that finish the edges of the roof structure, providing both aesthetic appeal and crucial protective functions. These include the end herlin, sometimes referred to as an end purlin or gable purlin, the barge board, which covers the roof rafters at the gable end of the house, often decorative, and the fascia board, a flat horizontal board located just under the edge of the roof, supporting the gutters and enclosing the ends of the rafters.
Fascia, barge board, the trim pieces at the edge.
Exactly. These components meticulously enclose the ends of the roof framing, contributing significantly to the building's overall weatherproofing and its polished, finished appearance. It's an incredibly engineered system, a truly finely tuned musical instrument, designed not just to shed water, but to withstand immense pressure from the sky, whether it's the weight of snow, the force of a strong gust of wind, or even the vibrations of a nearby train, keeping you dry and safe inside. So given all those intricate components for the framing system, what's the distinction between that detailed internal structure and simply roofing as a general term in our source?
Yeah.
Seems like there's a primary layer and then everything that supports it.
That's a great clarifying question, and it highlights an important conceptual difference. When our source refers to roofing in this broader general sense, it's talking about the overhead surface of a room used to conceal the floor above or the roof, but more specifically and critically, it refers to the outermost protective layer of the roof assembly.
The shingles or the metal sheets.
Exactly. It's the material that provides the primary watertight barrier and direct protection from all the elements rain, hail, snow, and direct sunlight. While the roof framing system, all those trusses, rafters, purlins, and braces, provides the essential structural integrity, the overall shape, and the robust support for the entire assembly, the roofing is the actual protective covering itself. It's the material like the GI sheeting, the clay tiles, the asphalt shingles, or the metal panels that we actually see from the outside, and that is solely responsible for shedding water away from the building.
Okay, so framing is the bones, roofing is the skin.
A perfect way to put it. One is the skeletal support, the other is the essential waterproof skin that keeps the elements at bay.
And often, that incredibly complex roof structure, with all its trusses and purlins, gets completely hidden from view on the interior by what we call the ceiling, which has its own system. V-interior overheads, ceiling framing. And speaking of concealment, let's talk about ceilings. Most of us just see a flat, painted surface above us, perhaps with a light fixture. But just like every other part of a building we've meticulously explored today, they're far more than just a simple surface, aren't they? They have their own structural components and serve multiple hidden purposes.
That's absolutely right. The ceiling is much more than just a decorative element or a simple cover. Our sources describe ceiling framing works as providing the overhead surface of a room, which is primarily used to conceal the floor above or the roof. But beyond pure aesthetics and hiding the rough structural elements, a properly constructed ceiling serves numerous vital functions. It provides a flat, stable surface for attaching lighting fixtures, ceiling fans, or even essential safety elements like smoke detectors and sprinklers.
Right, you hang stuff from it.
Yes. It also often strategically conceals intricate ductwork for HVAC systems, electrical wiring, and plumbing pipes, creating a neat, finished interior appearance. Furthermore, it plays a role in acoustic control, helping to dampen sound, and can contribute to the building's overall fire resistance.
Hides all the messy bits, too.
Precisely. The primary structural components of a ceiling are the ceiling joists. These are precisely defined as a series of beams to which the ceiling is attached. Our sources thoughtfully break them down into two types. Primary ceiling joists, which are the main supporting joists that span across the room, carrying the bulk of the load.
The main ceiling beams.
And intermediate ceiling joists, which are often shorter joists nailed between the primaries to provide additional support, particularly for the ceiling boards themselves, ensuring a consistently flat and stable surface. The diagram illustrates them typically spaced at precise intervals, such as 600 mm OC, on center, which ensures uniform support and prevents unsightly sagging or cracking in the ceiling material.
Spaced out again, like floor joists.
Similar principle, yes. To further prevent sagging, especially over longer spans or where the ceiling boards might be heavy, or if additional loads like insulation are present, hangers are critical, often unseen components. These are elements that support the ceiling where it tends to sag, effectively connecting the ceiling joists to the more robust structure above, such as the roof trusses, the rafters, or the floor joists of the level above. They essentially suspend the ceiling, ensuring it remains perfectly level and stable over time.
Like little supports holding it up from above.
Exactly. Finally, the visible surface itself is formed by the ceiling boards. These are the boards attached to the ceiling joists that create the finished, smooth, and aesthetically pleasing surface we see in paint.
The drywall or plaster on the ceiling.
Correct. So while much of its work is hidden, this system ensures a stable, level, and aesthetically pleasing overhead surface while intelligently hiding all the rough structural elements and essential utilities above it. 6. Openings and transitions. Windows, doors, and stairs.
We've meticulously built the shell, defined the interior spaces with walls and ceilings, and ensured a solid base and a protective roof. Now we need to address how we actually get in and out, and how we let light and fresh air into these enclosed spaces. That brings us to the dynamic, interactive elements of a building. Windows, doors, and stairs. These are far more than just simple holes or pathways. They are engineered systems that facilitate movement, expertly control the environment, and often, quite significantly, define the aesthetic character and welcoming nature of a building.
Indeed. These elements are the crucial bridges that connect the interior environment to the exterior world, or cleverly allow vertical passage between different levels within the building. They are profoundly functional, but also provide crucial security, vital comfort, and contribute significantly to the building's overall architectural expression. Windows and doors.
Our sources beautifully describe windows as openings in an external wall of a building to admit light and air, and doors as barriers which swings, slides, lifts, or folds to close an opening in the wall. They're clearly indispensable for both daily functionality and fundamental safety. What are the core components of their frames, and what are some common types we should understand?
Both windows and doors, despite their different functions, share remarkably similar fundamental frame components that ensure their structural integrity and proper operation. Starting with the overall opening in the wall, you first have the rough frame, which is the precise structural opening in the wall that creates the necessary space for the entire window or door unit to be installed.
The hole in the wall, basically.
Essentially, yes, but precisely framed. At the very top of this opening is the header, which can also be called the window head or door head. This is the uppermost member of a door frame or window frame, and it's absolutely crucial as it provides direct structural support, efficiently carrying the weight of the wall directly above the opening.
Like the lintel in a block wall.
Exactly the same function. Without a properly sized header, the wall above the opening would simply sag or collapse. Along the vertical sides of this opening, meticulously forming the edges, you have the jambs, which are defined as the vertical members on both sides of the opening, where the window sash or door slab will be securely installed and operate within.
The sides of the frame.
Correct. And at the bottom of the opening, specifically for windows, you have the sill, or window sill, which is the lowest member of an opening frame. The sill is meticulously designed with a slight slope to shed water away from the opening, preventing it from pooling and potentially seeping into the wall below.
Sloped to let water run off.
Makes sense.
Critical detail. Now, when we look at specific window types, our sources provide excellent illustrations showing the diversity of design for different functions. The jalousie window, for example, is uniquely characterized by its jalousie blades. These are the horizontal slats, typically made of glass, that pivot open like Venetian blinds.
The ones with the little cranks and glass slats. Right. They are particularly effective for providing excellent ventilation in tropical climates, as they can be left open even during light rain. Then there's the classic casement window, which features a large, often undivided pane, the single sheet of glass, or sometimes divided by slender muntins, vertical or horizontal separating panels that create smaller glass sections within the sash. It has robust top-bottom rails and a strong lock style, and it swings open outwards or inwards like a miniature door, often providing full, unrestricted ventilation.
Swings open like a door.
Got it. Finally, the sliding window is fairly self-explanatory in its operation, using a slide rail system for horizontal movement of its panes, often preferred for spaces where an outward swinging window might be obstructed.
Slide side to side. Okay. What about doors?
For doors, our sources show the solid panel door as a common and widely used type, illustrating its precise anatomy with a robust lock style, the vertical edge where the lock mechanism is securely installed, a strong middle rail, a solid panel, the main, often decorative infill, and clearly defined vertical rail and bottom rail that form its sturdy framework.
So the different parts of the door itself.
Yes. For swinging doors, you also have the hinge style, the vertical edge where the hinges are firmly attached, allowing the door to pivot, and the hinge rings, the cylindrical components of the hinges themselves that allow rotation. Other common and essential parts include the doorstop, a small strip or block that prevents the door from swinging too far into the room, and the escutcheon, which is often a decorative plate, typically found around a keyhole or door handle, adding a finishing touch to the hardware.
The little plate around the keyhole.
Exactly. These elements, from the robust headers to the intricate hinge systems, are far from simple holes in a wall. They are expertly engineered systems that provide precise control over light, airflow, security, and access, while contributing significantly and thoughtfully to the building's overall aesthetic and functional character. And to gracefully navigate between different floors within a building, whether it's a two-story home or a multi-story commercial building, we rely on stairs. They seem like such a straightforward, almost primitive part of a building, but just like everything else we've meticulously discussed, there's a surprising amount of specialized vocabulary, precise components, and critical design considerations that make them functional, safe, and even beautiful.
Absolutely. A stair is far more than just a series of steps. It is precisely defined as a series of steps connected by landing which permit passage between two or more levels or floors.
Yeah.
They're complex architectural features that demand incredibly careful design for both their fundamental functionality and, most importantly, for the safety of those who use them.
Okay, let's break down the parts. What holds the steps up?
Let's break down their key components, revealing how each part contributes to the whole. The main diagonal supports, forming the very backbone of the entire staircase, are the stringers. These are robust beams that support the steps and form the sides of the stairs. They bear the weight of the treads, risers, and users, transferring it down to the floor structures.
The sloping side pieces.
Correct. Resting horizontally and precisely upon the stringers are the treads, which are quite simply the horizontal steps. This is the crucial part you actually walk on.
The part you step on.
Yes. And vertically connecting one tread to the next, maintaining consistent step height, are the risers, which cover the space between two successive steps. These are the vertical parts of each step. Maintaining uniform riser heights is paramount for safety, preventing trips.
The vertical bit between steps. Tread, riser, tread, riser.
Exactly. For fundamental safety and crucial support, particularly on open staircases, you have the handrail, which provides a guard and form the ends of the balusters. This runs gracefully parallel to the inclination of the stringers, offering something secure to grasp as you ascend or descend, providing stability and confidence.
What you hold on to.
Right. Supporting that handrail and often contributing significantly to the aesthetic design of the staircase are the balusters, which are small posts supporting the handrail. They provide the necessary vertical support and often fill the space between the handrail and the treads, acting as a protective barrier to prevent falls.
The little posts holding up the handrail.
Yes, the balusters. At the very ends of the handrail, typically at the top and bottom of a flight of stairs, are the larger, often decorative, newel posts, which are the supports of the ends of the handrail, providing crucial stability and a visual anchor for the entire handrail system.
The big posts at the top and bottom.
Correct. Finally, for longer staircases, or those that change direction, a landing serves to break the flight of stairs, providing a flat, level platform for rest, for changing direction, or simply for a momentary pause between sections of the ascent or descent.
The flat bit in the middle or at the top.
Exactly. Each part here, from the unseen stringers to the decorative newel posts, is absolutely essential for creating a safe, comfortable, and easily navigable ascent or descent within a building. 7. The finishing touches. From raw structure to refined surface.
Finally, after all that incredibly complex structural work, laying the foundations, meticulously framing the walls, constructing the floors, raising the roof, and thoughtfully putting in all the openings, we arrive at the parts we actually see and touch every single day. These are the finish trims, the details that brilliantly transform a raw utilitarian structure into a polished, habitable, and aesthetically pleasing space. They're the elements that give a building its unique character, its visual refinement, and its completed, sophisticated look.
Precisely. Finished trims are meticulously defined as the visible woodwork or plasterwork or moldings of the building and room which covers or protects joints, edges, or ends of another material. Their purpose is beautifully dual. They provide immense aesthetic appeal, adding elegance and design flair, but critically, they also offer practical protection. They discreetly conceal unsightly rough joints where different materials meet, provide smooth, clean transitions between surfaces, and robustly protect exposed edges from wear and tear, physical damage, or, in many cases, from water intrusion.
So, pretty impractical. Exterior trims. This is where the building truly gets its distinctive character on the outside, isn't it? These exterior trims can be purely decorative, adding architectural style, or they can be absolutely vital for weatherproofing and long-term durability. What are some of the key exterior trims our sources highlight, and what hidden functions do they serve?
They are indeed crucial for both the form and the vital function of a building's exterior. Starting at the very top, beneath the roofline, a cornice is any molded projection which crowns or finishes the part to which it is affixed. These are often grand, decorative elements found at the top of walls, particularly below the roofline, providing architectural detail and a sense of classical proportion. But they also serve to subtly divert rainwater away from the wall surface.
A fancy molding at the top.
Often, yes. Then we have baseboards, which are pieces of boards nailed around the eaves and edges of the roof to protect the exposed parts of the purlins and rafters. They effectively trim out the lower edge of the roof, providing a neat, clean finish and, more importantly, protecting the exposed structural wood from weather and pests.
The boards under the roof edge.
Essentially, yes. Often the fascia and soffit system work together here. Around windows and doors, you'll prominently find caseboards and casings. Our source defines caseboards as pieces of boards placed around door and window openings to decorate, and casings as pieces of boards placed around door and window openings to decorate.
The trim around windows and doors.
Exactly. While these terms are often used somewhat interchangeably, both refer to the trim that meticulously frames these openings, providing a clean, finished look, and, crucially, covering the rough, unfinished edges of the wall and the window or door frame itself. They create a seamless transition and a refined appearance. For critical weatherproofing, which is paramount for a building's longevity, there's roof and flashing. This refers to GI sheet flashing of various designs placed at the ends of a gable or sloping type of roof, which serves to protect the end joints and provide watertight.
Flashing. The metal bits.
Yes, the metal bits are key. This is an absolutely crucial, often unseen element for preventing water from seeping into the structure at its most vulnerable points, like where the roof meets a wall, around chimneys, or it changes in the roof plane. Flashing diverts water away from these penetrations. Similarly, a drip cap is a piece of board placed above the window or door openings to make the water flow away from the opening and from other members below it, channeling rainwater out and away from the window or door frame, preventing it from entering the opening or staining the wall below, and protecting the longevity of the components.
Another piece to keep water out.
Water management is huge in building durability. Now, regarding those two terms we flagged earlier from the source, the water trowel and the Wheatmer board. As we suspected, these are very likely typos. The term water trowel is almost certainly meant to be water table. A water table is a piece of board or masonry placed at the bottom of the wall, typically with a projection that goes all around the building. Its primary function is indeed like a drip cap. It efficiently sheds rainwater cascading down the wall away from the foundation or the transition point at the bottom of the wall, protecting the lower structure from moisture ingress and splashback.
Okay, water table, not water trowel. Got it. And the other one.
And the Wheatmer board is most likely intended to be a weep hole board, or more generally, refers to weep holes themselves. As we discussed with CMU walls, these are those fascinating, small, deliberate openings placed below the water table, or at the base of wall cavities in masonry construction. Their main purpose is to allow any trapped moisture inside the wall system to drain out, preventing it from accumulating and causing hidden damage like rot or mold within the wall.
Right, the drainage holes again.
Exactly. These seemingly minor details collectively illustrate how trims are absolutely essential for both robust weatherproofing, protecting the building's integrity over decades, and giving a building a truly finished, durable, and aesthetically pleasing exterior appearance. B. Miscellaneous parts from the house and its parts diagram.
Looking back at our very first diagram, the house and its parts, it's an incredibly rich visual. There are so many labeled components we haven't explicitly called out in detail, but which tie so intrinsically into these larger systems we've explored. Let's make sure we highlight a few more specific ones that might not fit neatly into our previous categories, but are still vital to truly understanding the whole picture of a building. What catches your eye here as particularly interesting or commonly overlooked from that diagram?
It's true. That diagram is a treasure trove of detail, illustrating just how many individual components make up what we perceive as a single, coherent house. For instance, beyond the framing, it shows wall trim 11, panel 12, and exterior walling 10, providing further visual context for the outer skin of the building and how it's meticulously finished, often with layers that contribute to both insulation and weather resistance.
More detail on the walls.
Right. Within railing systems, beyond just the handrail and balusters, we can clearly see labels for vertical rail 7 and bottom rail 6, reinforcing the detailed, often custom construction of such elements that provide both safety and a distinct architectural style to balconies or interior stairs. And for the stair system itself, which we discussed in detail, the diagram labels every granular piece: handrail 5, baluster 4, newel post 3, stregger 2, tread 1, riser 1A, and even housing 1B, which is that precise groove or dado cut into the stringer to neatly receive and hold the treads and risers in place.
Wow, even the groove has a name.
Exactly. This emphasizes the meticulous joinery and assembly involved in creating a safe, silent, and durable staircase that can withstand constant foot traffic for generations. A couple of other critical yet often unappreciated elements tied into water management are highlighted. The downspout, 29, which efficiently carries rainwater from the gutter down to the ground. These are absolutely vital.
Gutters and downspouts, yeah.
While the roof sheds water, gutters and downspouts are the building's exterior plumbing system. Without them, rainwater would simply cascade directly down your walls, potentially eroding your foundation over time, or seeping into your basement or crawl space. They're literally diverting hundreds of gallons of water away from your building during a heavy storm, protecting its very base and ensuring long-term structural integrity.
Crucial for keeping the basement dry.
Absolutely. The diagram also shows the concrete footing 31, again reminding us of that crucial base. And tying back to the architectural elements of the roof structure, beyond the framing, the diagram points out the roof eave, 27, which is the part of the roof that elegantly overhangs the walls, providing crucial shade and additional protection from rain. It also shows the gable, 28, which is the triangular portion of the wall between the edges of a dual-pitched roof, often a key design feature.
Eaves and gables.
Right. And of course, reinforcing our understanding of the fundamental structural components, the diagram clearly labels the girder, 19, concrete post, 20, and column footing, 21, reiterating these critical load-bearing elements that form the hidden skeleton of the building. And to bring it all back to human interaction, we again see the window 22 and door 23 as discussed, showing their strategic placement as key openings for light, air, and access. Finally, reinforcing the roof structure we just dove into, it precisely labels the truss 15, purlin 16, and rafter 17.
So many parts.
Each of these numbered components, no matter how small, how specific, or how hidden, plays an indispensable and precisely calculated role in the overall integrity, long-term durability, and ultimate function of the house. It's truly a marvel of interconnectedness, where the absence or failure of even one small part can compromise the entire system. Outro.
So what does all of this mean for you, our listener? We started this deep dive by suggesting that a building isn't just a single, solid, static thing, but rather a profoundly complex collection of dynamic, integrated systems. This journey through the house and its parts and the meticulous methods of construction has, I think, definitively and quite fascinatingly shown us just how true that seemingly academic statement truly is.
It truly has. We've moved from a conceptual understanding of a building as a unified system, where every part relies on another, to the very granular details, from the ground-hidden footings that heroically bear immense weight, up through the varied framing methods of wood and reinforced concrete, the intricate hidden networks of utilities that power our daily lives, the nuanced elements of walls and ceilings that define our spaces, and finally to the protective and aesthetic finishes of the roof and exterior trims that give a building its identity. Every single component, no matter how small or seemingly insignificant, plays a crucial, interdependent role in creating a functional, safe, comfortable, and aesthetically pleasing space that we often completely take for granted.
Yeah, you really don't think about most of this stuff day to day.
Exactly. Understanding these relationships, seeing the building not just as a static object but as a living, breathing assembly of parts, is the key to truly appreciating any built environment you encounter. It transforms the ordinary into the extraordinary.
That's a powerful, truly transformative takeaway. Thank you so much for bringing these incredibly fascinating sources to us, allowing us to dive so deep into something so fundamental to our daily lives. It genuinely changes how you look at the world around you, how you appreciate the structures that stand tall.
And that's precisely the goal of the deep dive. The very next time you walk into any building, whether it's your own home, an office where you work, a bustling shopping mall, or a grand public structure, I encourage you to pause for just a moment. Consider all the unseen forces at play, the countless elements meticulously working together, each performing its specific function to create and maintain that space for you. What else might be hidden in plain sight, just waiting for a deeper look, a moment of curious inquiry?
Indeed. Keep those incredible sources coming and keep that curiosity sparked. We'll see you on the next deep dive.